It's yeast. It's in an anaerobic environment and it's alive. But if I want to know how well this yeast is able to metabolize the carbohydrate I'm feeding it and produce ethanol via fermentation, I need to use the wireless ethanol sensor with the display. Let me introduce you to it. Besides fermentation studies, you can explore the combustion of alternative energy sources and compare the vapor composition of simple solutions with the wireless ethanol sensor with display. It has a built-in data display, so you can either use it with or without data collection software. I've connected this sensor to SPARKvue, so it's easier for you to see the readings, but the sensor is also compatible with ChemView and Capstone. Included with the sensor are a custom number 6 one-hole stopper that's used to hold the sensor in place above a liquid. This is a gas sensor, and neither the sensor nor the probe should be submerged in a liquid or be allowed to get wet. The sensor also comes with a roll of Teflon tape if you need to replace the thin membrane that covers the probe below the cap. And it has a small bottle for calibration, so you can calibrate with a small amount of 1% ethanol. The sensor can be calibrated in any container, but we provided this small vessel to speed up wait time for liquid-vapor equilibrium. The sensor is factory calibrated and will only need calibration before a quantitative analysis, or if the sensor is not reading within 0.01% of zero in ethanol-free air after it has warmed up. As with other gas sensors, the wireless ethanol sensor with display needs a few minutes to warm up. Then after warm-up, you can take measurements. I've added a 2% sucrose solution to the flask, and I'm fitting the included number 6 one-hole stopper to it. I have a 2.7% by mass solution of active dry yeast in spring water, warmed to about 35 degrees Celsius, being stirred slowly to avoid splashing, and I want to know the fermentation rate when it consumes sucrose. I will add a 20 milliliter sample of yeast to that solution in the flask. Now I'll carefully place the probe in the system. And I'll turn on the stirrer to mix without splashing. Like any gas sensor, give it at least 1 minute to equilibrate to its new surroundings before you begin collecting data. Notice that the probe is a few millimeters above the liquid and are not letting the sensor get wet. While we wait, I want to mention that the sensor range is between 0 and 3% ethanol, so it will be necessary to estimate quantities expected above 3%. I will show you some tools in SPARKvue that can help with that. After 1 minute of equilibration time, I can start collecting data. I'll do a 15-minute run of data, and we'll speed through data collection for you. Since this data looks fairly linear, I can apply a linear fit to the entire run to estimate the rate of fermentation using the slope m, which in this case equals 1.72 times 10 to the negative 4% ethanol per second. I can use the linear fit to project beyond the recorded data to see how long it would take to reach 5% ethanol if the current rate of fermentation stays constant. I'm manually changing the range of the y-axis until I see 5%. And then I'm going to move the x-axis and manually scale that until I see the best fit line intersect at 5%. And I can change the units on time either to minutes or hours. It looks like hours would be more appropriate here. And I see that to reach 5% ethanol, about 5%, it would take about 8 hours at this rate. Go to PASCO's experiment library to find a lab investigation with a comparison of 2% sucrose as the yeast's energy source for fermentation with a 2% starch solution as an energy source. Thanks for watching, and cheers!